Hello everyone, my name is Rastio Kralovic, I'm from Comenius University in Bratislava, and together with my colleagues from Bratislava and Zurich and Aachen, we have some results about non-uniform finite automata. So in a very broad context, the uniformity is the property of a computational model that the same finite device is used to process all inputs of all lengths, that means infinitely many inputs. And some models, like Turing machines, are inherently uniform. Other models, like circuits, are inherently non-uniform. And the uniformity, of course, plays an important role in what can be computed by these devices. So it's a concept that has been widely studied. And there are also, in order to compare the models or to study the impact of non-uniformity, we have also non-uniform versions of uniform models like non-uniform Turing machines and uniform versions of non-uniform models like uniform circuit families and so on. So in this talk we will be speaking about non-uniform versions of weaker uniform computational models. So let's start with the Turing machines. The standard stuff is that so we have a family of Turing machines such that for each input length we use a different machine from this family. And since Turing machines are powerful enough to possess the universal Turing machine, Karp and Lipton noted in '82 that this definition is equivalent to a definition when we have the input which is prefixed by a string called advice, which is just an arbitrary function, only depends only on the length of the input. So this is the advice and then this is the input word, and you can think of it as a description of the machine that is used to process words of this length. So it's immediately seen that these two definitions are in fact equivalent. So the question is, what happens for weaker computational models that don't possess the universal machine? And then these two definitions don't have to be necessarily equivalent. And what about the non-uniformity in weaker models? And if you look into literature, there hasn't been that much work done. Notably, in 1982, Ibarra and Ravi Kumar studied the space complexity of the below log n range, and their model was that they had a family of two-way finite automata such that they were used to process the slice of the language of length n, and they looked at the number of states. So this Sn is the state complexity. We have 2 to the Sn states. And basically what they showed that there is a hierarchy from 1 to n, because of course with exponentially many states any language, any finite slice can be recognized. So they show the smooth hierarchy, so the log n threshold from the uniform complexity is not the case here. So then for the Karp-Lipton-like definition, Dam and Holzer studied in '95 finite automata with the same setting. So we have the input word and it's prefixed by some advice string. And of course, since we have finite automata, it doesn't make sense to have more than a constant, but still there is a hierarchy of languages that can be recognized. But of course there are some languages that cannot be recognized, and for example WW, as was proved there, and it means that this definition is in some sense strictly weaker than the Ibarra-Ravi Kumar definition. So in order to overcome this obstacle, there have been various attempts. Notable series of papers is by Tadaki and co-authors from 2010 and 2014, where they have the advice written in on a separate track, so like above each input symbol there is one advice symbol, which is nice because it does not introduce new resources like new tapes or new heads, but on the other hand you are still quite restricted in what sizes of advice you can process. And also a notable paper from 2010 by Freivalds, he uses a slightly different model of advice. For him it's just a use case of a broader concept, so it's really an insightful paper. So what we use is a model introduced in 2014 by Kucuk and others, where basically the advice is written on a separate tape. So we have a two-tape machine. The input word is on one tape with a delimiter. We will be dealing with one-way machines, so there is only one delimiter here. And the other tape, again a one-way tape, contains an advice, again delimited, but it doesn't matter too much. With this model, we have some interesting properties. For example, if the automaton is allowed to be non-deterministic, then any language can be recognized with exponential advice. Also, if the automaton is allowed to be two-way on the input tape, again all languages can be recognized. However, if we restrict on a one-way deterministic machine, one way on the input, suddenly there are languages that cannot be recognized. Again, for example, WW cannot be recognized. So since there is this gap between determinism and non-determinism here, it's a natural question, what about randomization? So if this automaton is one-way randomized automaton, how does it fit between the deterministic, which cannot recognize all languages, and non-deterministic, which can? So in this paper we address this role of randomization here. And for randomization we use the standard model of two-side isolated cut point at 1/2. That means we want an automaton that if the word is in the language, we are accepting with probability 1/2 plus some epsilon, and otherwise we accept 1/2 minus some epsilon, which is standard. Okay, so our results can be visualized like this. So first, we show that if we have deterministic automata, they cannot use more than polynomial advice. So any language can be recognized either with polynomial advice or cannot be recognized at all. And then we also show that this carries over to probabilistic automata. So again, they cannot utilize more than polynomial advice. And then we can show this strict inequality here. Basically, how we show it is that we consider this language, which is the language of words that have the same number of A's, B's, and C's. And it has been known about this language that it can be recognized by probabilistic machine with linear advice, basically using some more or less standard tricks from the randomized computation area. And what we show is that this language cannot be recognized by a deterministic machine with polynomial advice, which means it cannot be recognized at all. And the proof here is based on the fact that if there is an automaton that recognizes this language, the input is one way, so the automaton must somehow remember the equivalence classes of the prefixes, and there are quadratically many equivalence classes, and it can remember them just in the state or by position on the advice tape. However, since it's a deterministic automaton, it cannot navigate the advice tape arbitrarily, and then when it's computed properly how the navigation on the tape can be, we can arrive at the result that we need more than polynomial size of the advice in order to recognize this language. So this is one strict inequality that separates randomization from determinism. For this inequality, it has already been known that there are some languages that can be recognized by non-deterministic automaton with polynomial advice, but cannot be recognized deterministically. We just improve this advice size by noting that basically the complement of this language can easily be recognized with linear advice by a non-deterministic automaton, but since the deterministic automata are closed on the complement, it cannot be recognized by a deterministic automaton. So we have this strict separation between determinism and non-determinism with polynomial advice. Further, for this, it has been already known that, for example, WW cannot be recognized by non-determinism with polynomial advice, and of course, non-determinism with unlimited advice can recognize all languages. So this is again a strict inclusion. And for the last one, for comparing probabilistic computations with polynomial advice, which means all of them, and non-determinism with polynomial advice, we basically note that the language WW can be recognized by a randomized machine with cubic advice, and this is basically a restating the fact that there is a communication protocol with public random bits for equality. So when we have this, then we have a language that can be recognized by a randomized automaton and cannot be recognized by a non-deterministic with polynomial advice. Further, we have another language which is basically a non-equality, so we have the U and V, and we won't have an index where they differ, and it's easy to recognize this language non-deterministically with polynomial advice. On the other hand, again, there is relying on some lower bounds on communication protocols. We argue that this language cannot be recognized by a randomized machine with polynomial advice. So when we restrict the advice to polynomial size, then non-determinism and randomization become not comparable. And also we have, of course, this strict inclusion here. There are some languages that cannot be recognized by randomized automaton. So this is basically the overview, and now let me just briefly sketch some proof ideas. So from this first part, that we show that the deterministic automaton cannot use more than a polynomial advice. Well, the proof goes as you would expect. So imagine we have a deterministic automaton that works with some advice, maybe very long advice, and then in the computation, if some states are repeated, then we can somehow cut out this part of the advice and shorten it, and retaining the same computation. However, the main problem here is that we use the same advice for exponentially many words of the slice of the language of fixed length. So if you just compute it straight away, instead of polynomial size, you get here something exponential. So we must be more careful in finding the ways how to shorten the original advice. And what helps here is a simple visualization, so we can visualize the computation as a band of dots. So here on the x-axis we have the positions of the advice tape, and here on the y-axis we have the states. Now every processing of every word of a given length leaves a trace in this band, like this blue line here is a trace. So again, it's a sort of technicality that we can assume that the advice tape is real time, so it's moved in every step, so the automaton at the beginning is in some state and then moves here and here and here. And sometimes, as indicated by these squares, the automaton moves also the input head. Everything is one way. So these squares are called active points, and the active points in this band are those that move also the input head. So every word has its trace, and this trace contains exactly n active points, because again, it's a normal form that the automaton reads the whole input. Now in this band we have exponentially many traces for exponentially many words, but they have the property that if they collide, like here is the blue trace and the red trace, if they meet, then they go together up to the next active point, because here it means that the automaton doesn't read actually the input tape, or if you want, it reads the same symbol on the input tape, and it comes here. So you sort of need one active point to separate the traces that collapsed. On the other hand, since this band is very narrow, it has only constant width. Even though there are exponentially many traces, they must collide a lot, because they use the same width. And now if you put these things together, you arrived at the fact that if you can compute it, that there are only polynomially many active points overall in this band. So even though there are exponentially many traces, there is only polynomially many active points, and that means that there are windows like this green one where there is no active point, and then these windows can be actually cut out from the advice, and the advice can be shortened, because on any word the automaton doesn't read the input here, so it's fully specified by the transition from these states to these states, and it can be replaced by a constant width table that just implements the transition stuff here. So again, if we started with an arbitrary long advice, using this idea, we can have a deterministic machine that uses only advice of polynomial size and recognizes the same language. Now, how this carries over to probabilistic finite automata? Start with an probabilistic automaton with some advice string, and it has the property that for each word, if you run this randomized automaton on this advice string, you have probability 1/2 plus epsilon that it's correct. That means if it's in the language, it's accepted. If it's not in the language, it's rejected. So what we can do, we can encode the random choices of the automaton into strings. Now this must be done with some care, because we allow arbitrary probabilities of the transitions. So this must be some technicalities are here to be addressed, but it's not surprising that we can encode the computation, the choices of the randomized machine into some bit strings here. So what have we? Now we have a set of advice strings and a deterministic machine, such that if we fix any word and we choose a random string from this set, then the deterministic machine with this probability, now the probability is over the random string, then the machine is correct. So from this exponential set of strings, for each word there is a fraction of 1/2 plus epsilon that are good for this word. Now there are two problems. The strings are maybe long and there are many of them. But what we can use, the previous theorem, because now this machine is deterministic, so for the deterministic machine, each of the strings can be shortened to a polynomial length. So now we have possibly exponentially many strings, but each of them is of polynomial length. And finally, we can use Chernoff bounds to argue that if for each word there is a fraction 1/2 plus epsilon sets that are good, then we can select a polynomial set of these words such that for each word a slightly smaller fraction, but still 1/2 plus some other epsilon of them is good. So what we have now is a polynomial set of strings such that for each word, if we pick a random string from this polynomial set, it will be good for our finite automaton to accept or reject. And finally, we can construct again a probabilistic automaton that in a way that we just concatenate all these polynomial strings. So we will have advice of polynomial size, and this probabilistic automaton just goes over the advice string and picks at random one of these advice strings and simulates the deterministic machine with this particular advice, and so we have the acceptance probability 1/2 plus, slightly smaller epsilon, but still okay. So yes, this was like a rough sketch of the ideas that we have here, and this basically closes the main question about how the randomization fits between determinism and non-determinism. And of course we can try to make a more fine-grained analysis, like how much advice is used by non-determinism to be as good as randomization and vice versa. And of course what would be very interesting is to transfer these results to two-way machines, because of course the state complexity, the original idea of non-uniform space complexity uses two-way automata, and for two-way automata also the determinism can recognize all languages with enough advice. So the trade-off between determinism, non-determinism and randomization for two-way automata would be in my opinion very interesting to have. And also one can consider other non-uniform version of other models like push-down automata and other different devices. So yes, that's all from my part, and if you have any questions, then tune in during the Q&A session, or just contact any of the authors. The emails are on the first slide. And thank you for watching, and take care.